Morning, everybody. How are we doing? How's chapter 9 hitting you? You got through the easy problems. That's good, right? Some of you are like, chapter 9, I'm still in 7, right? We have a visitor today. Miss B is here to grade me, right? So all the complaints you want to lodge, you can see her after class, right? Miss B teaches biology. She teaches anatomy and physiology mainly, and has been at Fresno State College for, we decided, 6 years. Yeah, so I'm excited. I love actually getting evaluated because I get to be told what's going right, what's going wrong, all that kind of stuff. I was told by my dean that you should get an email next week that has the link for you to evaluate me, right? When you get that evaluation email, click on the link. Please dedicate like 10 minutes to filling it out. I'd love everybody's input, even if you just do the simple like rate, 1 to 7, whatever. To me, one of the favorite parts of my evaluation is when they finally show me all the student comments, right? They go through and they kind of strip out identifying information, so I don't know who it is. And then I love reading like what you wrote, right? So please, in there, put down whatever you feel is going right or wrong with your experience here in physics. I treasure those quite a lot more than I treasure the rest of the evaluation process. So if you could do that for me, I would appreciate it. We were halfway through chapter 9, sort of. Be honest. Tuesday was what? Thumbs up, thumbs down? It's a big thumbs down, wasn't it? Torque is nasty, right? Static equilibrium is nasty. We're going to do energy today in rotation. So we're going to go back. We're going to think about what we learned about energy for stuff moving in straight lines. And now we're going to do it in rotation. And then we're also going to do conservation of momentum. General feeling I usually get from students is that energy, while hard, isn't as hard as, say, Newton's laws, right, with all that kind of stuff. So it's a little bit of a breather here, but it's still a lot to be sort of swallowing in one chapter. What's happening next Tuesday? Test. Not the test. Almost. Review, right, for the exam. And again, review is where you come and ask me questions. And then what's happening on Thursday? The exam, right? We're going to do a lab on moment of inertia on Wednesday next week. Chapter 8 homework is due this Saturday, right? But hopefully you're done with that already, right? And really focusing on chapter 9, because chapter 9 homework is due on Wednesday of next week. Okay, we got all that in the bag. All right. Please tell me this is still working. Did this flip? Yes. Okay. Kinetic energy. Anybody remember mathematically how we wrote it down last time? No. That's being honest. Yeah, good. 1/2 mv squared. M for? Mass. V for? Velocity. All right. So let's pull a Google Translate. You remember Google Translate for the rotational kinematics? Do you remember that one right there? It was a way of getting from like tangential velocities for things going in circles to angular velocities for things going in circles. So let's do a real naive Google Translate, right? We have 1/2 mv squared. So we're just going to chuck things in here, right? 1/2 m, do the substitution, r omega, quantity squared. Let's rearrange slightly. 1/2 mr squared, omega squared. Uh-oh. You guys remember what mr squared was? Good, moment of inertia. Right? We talked about this last time. Do you remember where was the right? This table of moments of inertia and objects and simple objects and all that kind of stuff, right? Okay. So what we've got sitting right here is moment of inertia, the sort of generic definition of moment of inertia. So what we're going to do, we're going to say our rotational kinetic energy is going to be 1/2 times the moment of inertia times omega squared. So just like we did with kinematics, where we had the Remember how we had the kinematic equations and then we went to a toga party? And we wrote everything down in Greek for the rotational parts? We've dressed up kinetic energy the same way. Okay? Things that have rotational kinetic energy, right? They're spinning. But the thing about it is, and I forgot my big bicycle wheel, so I'll just have to use this small one, right? If this thing is spinning right here, it has rotational kinetic energy. But does it have any 1/2 mv squared? In other words, is it doing this? No. So 1/2 mv squared would be if the center of mass was moving. Okay, if I take it and I roll it, can't roll it, okay? If I take it and I roll it, now what does it have? It has 1/2 mv squared because the center of mass is going places, but it also has what? 1/2 I omega squared. Has panic set in already?
Yes.
Yeah, right, okay. So let's jump in, full force, no lifeguards, we're just going into the deep end, right? And then we'll rescue the swimmer, okay? The big equation in conservation of energy. Does anybody want to try and guess or remember it? Well, no. It started with work non-conservative. Oh, okay, right. It was final energy minus initial energy. Remember, that's like the master equation that we start with whenever we're working conservation of energy through a system. Okay, so what was work back in the day?
Jobs.
FD, and then there was cosine thetas in there, but we usually ignored the cosine theta and just did FD. You want to guess as to what the angular version of work might happen to be? Oh, good. So instead of, where would the theta, what's the theta taking the place of? D, right? A displacement, because it's that theta is what we connect to things that are going places, right? So work in rotation, it's going to have a theta, but before we get to the theta, which is going to replace D, what's a rotational force? We did it last Tuesday. You've already forgotten it because it's so bad. Torque. So we have a way to talk about the work that's done on a rotating object. Apply a torque to a propeller, and if it rotates through a certain number of revolutions, we can calculate how much work in joules was done to get that propeller going. Okay, so what does sort of the whole, like if we wrote out the entire conservation of energy equation in all of its glory and all of its parts, what might that look like? When we did energy final, what was the question we were asking? Good. Is there kinetic energy there? Is there potential energy there? So I'm doing this in general. I'm not talking about any specific situation, but in general, it's possible that something can have kinetic energy and potential energy at some final state. So we add a new question because we ask, is it moving? Right? Does it have 1/2 mv squared? But now that we know about rotational kinetic energy, what do we have to add? 1/2 I omega squared. So these would be the finals plus mgh final. So I've got kinetic energy final, like translational, right, in a line. And then I've got kinetic energy final, but this is the rotational version, isn't it? And then this is my potential energy gravitational. And then we would subtract off exactly the same thing, but for the initial state. And we'll do some examples here in a second. So 1/2 mv initial squared plus 1/2 I omega initial squared plus mgh initial, right? So like there's the worst it can be. Well, for now, until next chapter. And so you ask, what's the new question? Before we asked, is it moving? And where is it? Is it at zero for gravitational potential energy? So we're adding a third question now. What's the third question? Is it rotating? Because if it's rotating, we're going to have to include that energy that's tangled up in that rotation. Let's do an example. Let's see if we can't sort some of this stuff out by doing an example. We're going to do a bowling ball on a frictionless ramp, and then the bowling ball, oh, this is a compare and contrast problem. Okay, so let's see. Let's just draw a dotted line right down the middle. So a ramp, what does a ramp look like in physics? Oh, yes, right. So there is, you know what, I'll make that a little bit bigger because I've got a little bit of space, and I'm going to try and cheat here. I love electrons. Copy that and paste it over here. Okay, so we got the same ramp. Okay, what's the difference? This one's got no friction, and this one does have friction, right? Okay, so if there's no friction on the hill, there's no friction on the ramp, does the bowling ball gonna roll? If there's no friction, and it's on a ramp, it's not going to roll. There's no reason for it to roll. Remember, rolling motion was all about the static friction between the two surfaces? Well, if there's no friction here, bowling ball is just going to slide down, okay? So everything we're going to do on the left is review from chapter, I can't remember what chapter that was, 6? Is that where we did energy? That felt like so long ago, didn't it? That's what torque does to you. Okay, so let's see here. We have a bowling ball, and it's going to start up there, and it's going to slide down, and it's going to get here. So I'm going to put initial point where it starts. I'm going to put final point. Where am I going to put 0? Top. You want to do top this time? No, it's not. Okay, all right. The rule of thumb Mr. Balogh always follows is put it at the lowest point in the problem, just so that we don't end up with negatives. You can put it at the top as long as you're consistent, but we won't practice that. Okay, so what next? Do you remember what we did next? We're doing conservation of energy here. Here's, well, okay, we don't need a free body diagram because it's energy, right? Free body diagram would have been for Newton's laws. Good, the master equation, right? That's really like, we got our visualization down, now we got to strategize, and the strategy is energy final minus energy initial, right? That's where we get all of our strategy, okay? Left side or right side first? You pick. Left side, work non-conservative. Is there any work non-conservative in the problem? Why not? There's no friction, right? No, and let's be really careful. Kinetic friction. Kinetic friction would be the non-conservative work. Because static friction, which allows for rolling motion to happen, turns out to be a conservative force. So don't worry about that one in the work non-conservative. So we're not going to have any friction, so therefore there is no work non-conservative. Are there any other forces? Are there any other propulsions or pushing or pulling or anything going on? No. Well, gravity, but that we don't do gravity in the non-conservative side, right? Okay. So, but yes, good to remember that. Okay. Final, there at the bottom. Is it moving?
No.
No?
We don't know.
Well, it's been sliding down the hill.
Yeah.
Yeah. So 1/2 mv squared. Please don't make me do a conservation of momentum problem 2 where it has to come to a stop. No? Okay, that's okay? All right, good. And then does it have any potential energy down there? No. Do you want me to write +0 or can I just leave it? Okay. Minus, and now we're going to do the initial energy, right? At the top, at its initial point, is it moving? Starts at rest. It's not going to have any kinetic energy. Does it have gravitational potential energy?
Yes.
Sure does. Let's solve for v. Right? Isn't that what they asked us to do? Compare the final speeds of each ball. Right? So we're going to solve for v in either case. All right. So, okay. I'll do the algebra this time. What happens to the mgh? Ooh, better yet, I'll move the 1/2 mv squared over to the other side. And it picks up a minus sign. And then with the two minus signs being on both sides, what do? Cancel those out. What else appears on both sides? Mass. V squared is equal to 2gh, which means v is equal to the square root of 2gh, right? Do you get the feeling that the square root of 2gh is following you around? It's kind of come up a lot, hasn't it? What's the speed of anything when it falls through a height h? Square root of 2gh. Does it matter if it does that or rolls? If there's no friction, so it does matter if it rolls. If it slides, right? If there's no friction, then it makes absolutely no difference, right? Its vertical speed would be the square root of 2gh. When you don't know, and you're lost, and you're drowning, right? And your homework is like holding you under, right? What are you going to reach for? Square root of 2gh. If you're going to guess, either guess 42 or the square root of 2gh. One of those is going to be the answer. All right. Some of you didn't understand the reference, did you? What's 42? Answer to life, the universe, and everything. Thank you. Okay. Go read the Hitchhiker's Guide to the Galaxy. That's your homework. Let's do with friction. Okay, so with friction, the ball here will be rolling down the hill. So we're going to have static friction. Because it's rolling without slipping, it has to be static friction. That's important. Is there any kinetic friction? Is there any sliding going on? No. So what is the work non-conservative going to be? If there's no kinetic friction, good. It's going to be 0. Okay? So, energy final. Oh, I didn't specify. This is, again, the initial. This is the final. That's 0. It rolls all the way down the hill. And at the bottom, right, it's still moving and rolling. Okay. So, at the bottom, what kind of energy does it have? First question. Is its center of mass moving somewhere? Yes. So it has 1/2 mv squared. Second question. Is it rolling? Yes. 1/2 I omega squared. Third question. Does it have potential energy? No. Why not? It's at the bottom, and we said the bottom was 0 for gravitational potential energy. Minus, and now we do energy initial. Up at the top, we're releasing it at rest. So is its center of mass moving somewhere? No. Is it rolling? No. Therefore, no kinetic energy up there at the top. There's no rotation, there's no translation. What does it have? Potential energy. Guys are rocking it today. Well, it was because Tuesday was so bad, right? This is a breath of fresh air. Okay. Oh my gosh. How do we solve that for V? I mean, Mr. Balogh asked a simple question. You just move it over, Mr. Balogh, and solve for it, right? Do algebra. But right? We've got I omega. So we've got to sort out two things, don't we? Ooh, we need Google Translate? Why do we need Google Translate? Because when something is rolling, the velocity of its center of mass is equal to the radius times the angular speed at which it is rolling. That was the kind of one of the big things about rolling motion that we talked about. I think it was back in chapter 8. So if that's true, we can figure out what omega is, right? Omega and V are linked to each other when something is rolling. Matter of fact, I'll put down because rolling. This is true, right? So this is going to go in right there. We'll just substitute in the omega. But we can't we got to solve for omega, right? So what's omega? Try again, V over R. Okay, so we can stick that in there. Okay, so what are we going to do for the moment of inertia? We can't do mr squared because we know something. This isn't a generic shape like going around in a circle. This is a full shape that's rotating on one of its axes.
Translate to M. No, wait, you said it's not true.
It's a bowling ball, right? So which one of these is the bowling ball? Solid sphere, H, right? Thankfully, somebody's done it for us already, right? They figured out what the actual moment of inertia of something that's solid and spherical rolling on its axis. Now, its axis isn't vertical like this picture. It's tilted over to the side, but that doesn't matter. It's turning around an axis. It's got to be this. So the moment of inertia is 2/5 mr squared. So that's what we're going to do. We're going to put it, so we know we looked at the table, not 1/2. 2/5 mr squared, right? Okay, this is from the table. And where's the table going to be on the exam?
Back of the block.
On it. You don't have to put the table on your cheat sheet. I will give you that table, right? The very table that I've been showing you. It's going to be the last page of your exam. So now I'm going to stick in the moment of inertia, right? It's this moment of inertia is coming in here. So what is that going to be? That's going to be 2/5 m. Real quick, is this m and this m the same m? Do we need to fight?
It's the same object.
It's the same object.
Oh.
So it's going to be the same mass, isn't it? Okay, so that's the same mass. The radius of the ball and the radius that we have up here in the Google Translate, getting us from center of mass speed to angular rolling speed, is the same r. Again, it's the same object, so the same radius of that object. So that's, I can use little r there. And then omega squared is going to be v over r. This has gotten worse. Right? I mean, well, speak for yourself, Alice. Right? Like, I mean, when friction's not involved, it's a beautiful day, isn't it? This is what friction gets you. But there's hope. Watch.
Flex you.
Is there an m in every term?
Yes.
What about this 2 and this 2?
Cancel out.
What about this r squared and this r squared?
Cancel out.
It's because I'm a physicist. All right. V squared. What's left? 1/2 v. That's not an r, that's a v. My bad. I got too excited. V squared. 1/5 v, right? That's all that survives. Did I get that right? 1/5 v squared, right? It's all. Oh, it's a good day. Living right. Ooh, and what's 1/2 plus 1/5? 7/10. Did I beat you? I can't do arithmetic, let alone fractions. Is that right? 7/10? Is the common denominator 10? It's 7/10 minus GH. Move the 7/10 V squared over to the other side, picks up a negative. The negatives cancel. V is going to be the square root of 10/7 GH. That whole mess turned into that? Which one of these is faster when it gets to the bottom? Red or the blue? They're not the same. If they were the same, these two expressions would be identical. They are not identical. What's the difference? One is 2, and one is 10/7. Everything else is the same. What's bigger, 2 or 10/7? 2. Which one's faster when it gets to the bottom? The one that didn't have any friction. But energy must be conserved. Do both of these bowling balls have the same potential energy at the top? Is MGH exactly the same for both of these bowling balls? Yes. So what must the kinetic energy in total be at the bottom? The same. Energy must be conserved. So both of these balls have exactly the same energy at the top. They have exactly the same energy at the bottom, but one of them is going slower. Why? It has to roll. So where did some of the kinetic energy go? Into the kinetic energy of rolling. If I had two identical objects, one of them was just moving along, not rolling. V, mass, radius, everything's the same. And I had another one, exactly the same, but it was rolling at the same center of mass speed. Do they have the same energy?
Yeah.
One of them is doing 1/2 mv squared, but the other one is doing 1/2 mv squared, same exact 1/2 mv squared, but also has rotation. Which of these has more energy? The rolling one, because the center of mass speed is the same. Here, the center of mass speed was different. The V we solved for is the center of mass V. It's the linear V. It's how fast it's going when it gets to the bottom. But some of that speed was taken up by the rotation. I'm glad there's a biologist in the room. She can correct me. Where's my pen? Field trip to Africa. Okay? Gazelles. What's a gazelle's main purpose in life? Get away. Right? And so they've evolved to be able to get away as fast as possible from the things that are hunting. What does a gazelle's leg look like? They're kind of long and thin, right? Okay? In fact, a lot of them, I'm sorry, this is not representative of anything, right? Okay? They kind of look like this. Okay? Not really, but you get the idea, right? Okay? The axis of rotation, and I know it's double jointed, don't care, okay, right? The axis of rotation, right, is up here, right? The gazelle's leg has to go around the hip, okay? Why put all of the mass up here? In other words, why is a gazelle's leg not shaped like this? Why does it take more energy to get this one rotating? The moment of inertia is different, right? This gazelle got eaten. No evolution for this one, not passing any genes along. This is a dumb gene, right? This one allows the leg to get into rotation faster or easier. And if they can rotate their legs faster or easier, what do they have more energy for? Translation. Or in the case of half of the gazelles, boing, right? as they take off and try to achieve orbit. So, bicyclists, okay? Bicyclists, they're kind of crazy, but everybody that does the sport's kind of crazy. So the ones that like race, what do they do to their tires? Not flatten them. Okay. Do they make them heavy or as light as possible? Like light as possible, right? I mean, the rest of the frame can be made out of carbon fiber composite. That's another story. But like the wheels themselves, right? They will go for some of the lightest materials. If they could literally make a tire out of air, they would. But they can't. They got to have some structure to hold the air in, right? But they'll make those tires as light as they possibly can. Why? So that the wheels don't take as much energy to get rotating. If the wheels don't take as much energy to get rotating, then what are they going to be? What can you use that energy for? Translation, right? Getting going. There's a certain amount of energy that the rider can put into the pedal, right? That's limited by their training and their physique and their fitness. But that energy gets divvied up between getting the tires to rotate versus getting the tire's center of mass to get going. And the less energy you can take in getting something to rotate, the more energy you will have to get it to translate. Get your quiz sheets out. Kind of feels like a while since we did one of these, huh? Ah, that's where I went. The last thing that we've got, oh boy, right? How you doing? Awful. Is it the, oh, well, you want to eat, that's different. Okay. But like physics-wise, like, how's this unit been? Kind of rough? What? Past couple, yeah, right? Like the unit before was pretty rough, and now this one. I kind of told you the second and third units are the rough ones, aren't they? But like compared to the last one, how's this one feeling?
A lot better.
Better, but some of you are saying worse?
I feel like it's like starting to divide off.
Yeah, this there's a 50-50 split here, right? In my classes, half the students say this is better and the last one was worse, and then the other population is the other way around, right? Okay. So don't let it get away from you. I know you feel like you're hanging on for dear life. The train isn't stopping. It's not letting you off, but you're also like barely hanging on. Keep going, okay? Yeah, the train does speed up, but it does get a little bit easier as we go. So let's deal with angular momentum. Does anybody remember what momentum was? Well, let's see, 2 chapters ago? That was only 2 chapters ago? I'll help you out. Linear momentum. Remember that? Okay. Things colliding, conserving momentum, physics sandwiches. Is any of this ringing a bell? Okay. So, angular momentum. Wouldn't it be really nice if instead of m we could just write moment of inertia? And instead of v, what would we write? Omega. Wouldn't it be really nice if that could be the case? Well, guess what it is? It's exactly what angular momentum is. Okay? Moment of inertia times angular speed instead of mass times linear velocity. Everybody knows that angular momentum is spelled with an L, right? I mean, it's obvious, isn't it? I'm not making this up. I'm not responsible for these symbols, right? I guess partially I am. I'm perpetrating them. But like, that's the symbol we use for angular momentum. Don't ask me why. Historically, somebody picked L. there's 26 letters in the alphabet. We got too many things to cover, right? So angular momentum, right, is that. It's also, and I won't prove it to you, but it's also MVR for anything that's moving, like circling around, like a tennis ball on the end of a string or something like that. You'll find that if you just put MR squared in there and then do the Google Translate, you'll get the same thing. That's beside the point. Okay. When we did momentum before, right, it was objects smashing into each other or connecting, like coming in and connecting together and then rolling. And there was inelastic and there was elastic and there was all this stuff, right? What's a rotational collision? Okay, yeah, something rolls into me. That is not a rotational collision. That is a linear collision because the rolling thing center of mass is coming at you in a straight line. That's MV. So two rolling things? No. The Balogh household, we don't watch very many sports, but we do watch the Olympics. Okay? And the Winter Olympics just happened. And what was her name? Was it Alyssa Liu, United States, won the gold medal for figure skating, women's figure skating. Figure skating is conservation of angular momentum. Let me explain. I am not Alyssa Liu. I have back and neck problems, but I'm going to attempt this anyway. Okay? You believe in me? Yeah. I brought my figure skating simulator with me. Okay. So I'm going to put that right there for now because I just need some room. In figure skating, there's lots of required elements, right? And one of those elements is that you need to do this motion, okay, where the figure skater starts with their sort of limbs outstretched, right? They got their foot backwards, right? Okay, and their hands are out like this, and they're skating in a straight line. And then how does this move end? They turn, they bring their arms and legs in, and now what are they doing? Whoosh, right? And in that spin, they do like bad things. They pull their feet up to their heads. They do all kinds of stuff, right? Okay, but and it's amazing and beautiful and all those things. But they will change like where their limbs are in that spin, right? Sometimes it'll be really tight, and sometimes they'll fling them out, and then they'll bring them back in again. And what happens to the rate of rotation as they do that? Speeds up and slows down. That is an angular collision. So the seat I have here, right, spins around, okay? I have here with me, okay, a couple of weights, right? And these weights are, sample for me. Is it heavy? Yeah? One person? Holding them over devices here, right? Is it pretty heavy? Yeah, okay, right? So these are pretty heavy, okay? I have physics muscles, which means I can't hold them out for too long, but I can't hold them out. So what I'm going to do on the chair is I'm going to bring them in, right? I'm going to start with them out here and then bring them in. The reason I'm holding weights in my hands is to magnify this effect, right? To make it much bigger than it would normally be, okay? So I'm going to start with them outstretched, give myself a little bit of speed, and then pull them in. And I'm going to go the other way so that I can unwind my brain. Right? Okay. Thank you. Thank you. Yeah, do I get a 10? Yeah. Then you get an A. Okay, good, right? Yeah. So, what's going on?
Kinetic collision.
There. Was there a collision? No. It's not like something slammed into something else, right? But something did change. What changed?
Your rate mass. So then your linear momentum reduced.
I thought Allison ate my pencil. Okay. That's not my chair. So what changed?
Displacement of mass to your radius.
Yes. In other words, you've got three things to pick from. The moment of inertia changed, changing the angular speed. But the thing that stayed the same? The angular momentum. The total amount of angular momentum that I started with and what I ended with was the same. We'll do that later. Let's do angular momentum, like linear momentum, must be conserved. What you start with is what you have to end with. What did I start with?
0.
Nope. I was spinning. I had some initial moment of inertia with some some initial angular speed. What do I end with? A different final moment of inertia and a different final angular speed. But their product, the multiplication between them, has to be the same. So if I solve this equation for omega final, it's going to be omega initial divided by omega final times omega initial equals omega final, right? And let's say that my final moment of inertia, okay, is, I don't know, 1/3 my initial moment of inertia. In other words, my initial moment of inertia was bigger, right? Okay, I'm going to end up with less. Here, I'll write it this way. Is this the identical thing? My initial is 3 times my final. Oops. This will just make the math just a little bit easier. Is that okay? So I'm starting, right, with my initial, with those weights way out here. And then I bring them in. And all I've changed is the radius, right? But in doing that, I altered the total moment of inertia of everything, me, the seat, everything. I changed it by a factor of 3. And by bringing it in, it got smaller. So I start 3 times bigger than where I end. Okay. So if that's the case, right, and I take this, right, and I stick it over here, what am I going to get? I'll get 3 I final all over I final. Omega initial equals omega final. And what's I final divided by I final? And I end up with omega final being equal to 3 times omega initial. So I changed the moment of inertia by a factor of 3. So what happened to my angular speed? It changed by a factor of 3. If one goes down, the other goes up, and vice versa. So an angular collision is not objects running into each other. It's moments of inertia changing. Look for where the moment of inertia changes when something is rotating, and then you'll know that you're doing a conservation of angular momentum problem. We're going to find the angular momentum of a kid on a merry-go-round. I put a picture of one up there because I'm just afraid that children in the United States don't know what these are anymore, right? Because they took.
Have one at River Park. It just sucks.
Is that what's going on?
They have one in the place at River Park, but it's a really crappy one. It doesn't go fast.
Yeah, it needs to go fast.
It does.
You need like a near frictionless bearing. Is there a park that has one?
It's like a new version of that. Instead of it going all the way to the ground, it's higher up,
Higher up?
and you have to self-spin.
Oh, no. What you need to do is you need to get all the big people on the outside, all the small people on the merry-go-round, have the big people push, big mass, push little mass. Whee!
And it's like a self-spinning one, and a lot of
There's a playground right there. Do you know how much it kills me that we are not allowed to go use it?
It's so sad.
I actually, when we were planning this building, I said, I want a playground right out here in the quad. You want to make college students happy? Give them 5 minutes on the swing. The memory of innocent days, right? When life was good and differential equations were not a part of things, right? Just give them that. They said no. I was like, well, but we need it for physics lab. They still said no.
a lot of parks don't have swings anymore.
I know. Swings are gone. The teeter-totters are gone. I know I'm an old man. Get off my lawn. But come on, bring back the fun toys. Okay, so we got a kid. Kid's going to be sitting on the edge of the merry-go-round. Merry-go-round's going to be going around, right? Okay. Maybe it's not a kid. Maybe 4 kilograms is more like a backpack. Okay. So I'm going to just draw a picture. Here's a top view of the merry-go-round. Here's the backpack sitting on the edge, and the merry-go-round is going around like that. Okay. Now, this is interesting. They gave us tangential speed. So we know that the backpack, like at this moment, which way is it going, up or down? It's going up. Right? There's its tangential speed, which is related to its omega, right? And they want to know, find the angular momentum, right? So we're just going to calculate the angular momentum. That's I omega. We're going to take the vectors off because we don't really care about directions. They just want what the angular momentum is, right? Okay. Okay. Did they tell us what omega was? No. So what do Google Translate. So the way to get from linear to angular terms is through there, isn't it? So omega is going to be v divided by r, and that's 5 divided by 2, isn't it? Meters per second. No, not meters per second. Radians per second. Okay. So we got the omega. How are we going to find the moment of inertia? The table. So does the table have an entry for a backpack sitting on the edge of a merry-go-round? We're not asking for the moment of inertia of the merry-go-round. We're asking for the moment of inertia of the backpack. We want the angular momentum of the backpack. It's not hollow because it's not. The backpack does not have a mass that looks like this. Right? Its mass is located at a single spot. And I've already told you, it's not on the table, but I've already told you what the moment of inertia is of something, a single object, going around in a circle. It's just mr squared. Okay? So you have a point mass like this backpack sitting on the edge. It's going to have a moment of inertia of mr squared. That's not on the table. It's not coincidence, but the thin-walled hoop, thin-walled cylinder, what I call a hoop, also is mr squared. But that's like the total mass of the hoop all added together. It's like an infinite number of backpacks all put together. No. No, the backpack is always just mr squared. What would the merry-go-round be? What would you guess from the table? Because the merry-go-round is mass spread out. It'd be whatever a solid cylinder is. Yeah, 1/2 mr squared. So we know, okay, so we know, I went and found the number, but let's find, so omega is equal to v over r, and I is equal to mr squared. So the angular momentum is going to be I, which is mr squared, times omega, which is v over r. Ooh, look, what happened? One of the r cancels, and do you remember I gave you mvr before? Well, there it is. So I can get it. I can either calculate the moment of inertia, 4 times 2 squared, 16? Yeah? 4 times 4 is 16? Kilogram meter squared. We got the omega. So what's 16 times 5 over 2? I have no idea. 40? And what is 4 times 5 times 2? They're the same. What are the units of angular momentum? I can't remember. Kilogram meters per squared divided by seconds. Kilogram meter squared from the moment of inertia. Radians per second for the omega. Radian isn't a unit. So either way, right? Either kind of use Google Translate to get it or just use MVR. They're identical. They're the same. You'll get the same answer. There's one example, and I didn't include it. I should have put the picture up. And unfortunately, do I have it here? Hold on a second. I may not have it on there, but I do have it. We're in chapter 9, right?
Yeah. No, we're chapter 16.
Yeah, you wish. Okay, let's do this. Sorry, YouTube people, you're not going to be able to see it. Oh, no, got to push play. Play. And et voila. Should come up now. Okay. Yeah, whoa! Bunch of biologists in the room going, No, this is the transmission of your car. Okay? Does anybody here know how to drive manual? Stick. Good. It's not quite dead yet, right? Okay. Most all of the cars are automatic transmission, meaning it does the shifting of the gears for you. Okay. What are the gears for? Go fast better. That's what a transmission does, right? Because if you didn't have gears, your car's engine would have to rev really high using a lot of gas in order to get your car to go. The shifting of the gears allows the car to run the motor at a lower speed but still maintain the speed. But a car can't do that initially. It needs more torque and things to get going, but once it's going, it can use less energy to keep the same speed. Transmission job is to change the gears that connect the motor to the tires. Why am I talking about this now? Every transmission needs a clutch. This is the clutch right here. It's a series of discs and pads. When you pull up to a stop sign, a stoplight, okay, and your car comes to a stop, does the motor turn off? No. And you got a fancy new car, some of them will shut off. And then when you're ready to go, it starts up really quick and goes. But in general, internal combustion car, motor doesn't turn off, right? It just sits there idling, right? So your car's engine is rotating. It's got pistons and it's got a big flywheel and the drive shaft and everything. It's turning around, right? It has to because eventually your wheels need to start rolling, right? So it's a whole bunch of rolling, rotating parts that while you're sitting there at the stop sign or the stoplight is disconnected from the wheels, right? Your foot's on the brake. The car is automatically disengage the motor from the rest of the drivetrain of the car. When you take your foot off the brake and put it on the gas, the car automatically shifts the gears, connecting the motor of the car, which is rotating, with all the tires, which go from not rotating to rotating. The clutch is responsible for that, bringing something that's turning, the engine of the car, meeting up with something that's not turning. They meet and then they start rotating together. That is the closest thing I can give you conceptually that is an angular collision. It is literally a rotating thing that meets with a non-rotating thing. They come in and they touch each other and they begin to rotate together. So if you want to have a picture of a rotational collision that's not a figure skater, it's this. Some of you are like, I'll take figure skater, Mr. Balogh. What was your question?
Oh, so is like gears would be an example of an angular collision?
Yeah. Gears meshing with each other and things like that are literal angular collisions because you're trading angular momentum between the different gears that are in the system.
Does it need to be, like in reference to the gears, like you were saying, they can't be in opposite directions?
Is somebody going to ask me now, how does reverse gear work? Because I'm not sure I understand either. Right? Okay. It has to do with the direction that the teeth of the gears are in the transit. We don't need to go there. Okay. But the clutch, this thing that allows engaging and disengaging of the wheels and the drivetrain from the engine of your car, right? Electric cars. Do electric cars need clutches? Nope. It's just a pedal connected to a motor, and if the motor turns, wheel turns. They're much simpler. I want to show, yeah, I've got time to do this. I want to show you something. Maybe. Yeah, okay. So first an apology, right? The apology is I was unable to bring this demonstration with me this morning, okay? I thought about it, but post my ablation in my neck still hurts, and this demonstration had a good chance of really tweaking my neck, okay? And the doctor told me to take it easy. Talked to him yesterday. I said, still hurts, doc. He's like, take it easy. We'll look at it in a couple days. So I'm taking it easy. So I grabbed a clip off the internet instead. Otherwise, I would have done this in front of you, okay? I do want to point out in the video you're about to watch, Dr. Derek Mueller of Veritasium YouTube channel. Highly recommend it. It's a good channel. He is extraordinarily stupid in this video because he's not wearing any kind of PPE, okay? You'll see what I mean here in a second.
I am here at the University of Sydney where the mechanical engineering shop has built this incredible piece of apparatus for me. It is a 40-pound, that is 19-kilogram flywheel on the end of a meter-long shaft. Can you imagine trying to hold this out horizontally with just one hand at this end? It is virtually, it is impossible, okay? I'm gonna let go. You're gonna hold it at all? Okay. Can you lift it out? Make it horizontal, hold it. Come on, just try to, I want you to hold it out horizontal. See if you can. Hold it. Oh, come on. What I'm gonna do is I'm going to spin this up to a few thousand RPM. And then I'm going to attempt just that, to hold it from one end and have it out horizontally.
The amount of energy in this wheel is terrifying.
I'm going to let go with my left hand. What you'll see is that the shaft remains horizontal. You can see it going around there.
It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel down to the ground as you'd expect, the weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyroscopic precession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more extreme.
I'm going to try to lift it over my head with one hand while it's spinning. Wish me luck.
But before I make the attempt, Rod wisely suggests that I first check if I can lift the wheel above my head without it spinning.
Let's prove that I can lift it just this end without it spinning. Here we go.
It's very heavy.
Awkward with the hand.
Careful.
Physics muscles.
Woo! Just barely. Oh goodness, do you even lift? Clearly I do not.
Undaunted by my lack of strength, I'm going for it. But I want to make sure that the wheel is spinning as fast as possible to give me the best chance of success.
Give it 10 more seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, go!
That was perfect. Now I am going to release my left hand and holding only with my right hand at the end of the shaft, I'll try to lift it up over my head. This is a 40-pound, 19-kilogram flywheel. Ready? Here we go. 3, 2, 1. Beautiful. Let's go again. In 3, 2, 1. Nice. 3, incredibly light as I do that.
So the question here is why? You saw that he couldn't really, it was really hard for him to lift that just straight up, right? But with that rotation, he was able to lift it pretty easy.
Is it the friction, the amount of force that's being caused by gravity is being reduced because of the
What did it not have when he just tried to lift it? Had, not torque. It was no angular momentum, right? But with it spinning, it had angular momentum, a truly terrifying amount of angular momentum, okay? With that angular momentum must be conserved, both magnitude and direction. With that spinning angular momentum, and gravity trying to torque it down, the wheel fought those changes. It wants to keep the same angular momentum, both the amount and the direction. Gravity wants to pull it down and rotate it around the axis. And so they fight each other, and they end up fighting each other in such a way that it precesses around, gyroscopic precession. And in that precession, it's almost as if its weight is being canceled out. Not quite, but pretty darn close. Angular momentum is weird, okay? And angular collisions are weird. Hold on to the fact that it's really just I omega or MVR. Hold on to either figure skating or the clutch in a car's gearbox, and you'll be okay. That was the end of chapter 9. We have from now until Thursday to pick up all of the pieces, right? I hope to see you in Grasp on Friday, tomorrow. See you then.